Okay, so hi everyone. Thank you for being here. Today we are really excited and really honored to present our speaker, Dr. Nilanjan Chatterjee. He is the Bloomberg Distinguished Professor of Biostatistics and Genetic Epidemiology at the Johns Hopkins School of Public Health. And he also holds an appointment in the Department of Oncology in the Johns Hopkins School of Medicine. So Dr. Chatterjee's research really covers a very wide range of topics in public health and medicine, and chief among them are his work in statistical genetics, cancer research, gene environment interactions, and something I'm particularly excited to hear about, data integration and meta-analysis. So among his very many awards, Dr. Chatterjee received the COPS Presidents and the George W. Snedeker Awards in 2011, and he is also a fellow of the ASA. So we are really just absolutely delighted to have him here today. As a brief reminder, talks are generally about 45 minutes. We'll try to schedule for about 15 minutes of questions at the end. Please remember to mute yourself, and I will try to keep an eye on the chat to catch any questions so that we can have a lively discussion at the end. And so with that, please share your screen when you're ready.
Yep. Just give me a second. All right. Can you all see my screen?
Yes.
Okay. Thank you. Thank you for the invitation. Thank you, Emily, for the wonderful introduction. And it's a real pleasure for me to virtually visit this department. And this is my first visit, I think, but hopefully my next visit would be more in person. And I know a lot of people from the department. I have a lot of friends, but it has been a while I've seen them since, because of the pandemic, we don't go to conferences anymore. But this is the next best thing we could have. So it's a real pleasure for me to be here. And so I'll be talking about an area of statistics that I'm very recently, I've been very passionate about for a long time, and actually going back to my PhD thesis, working on two-phase epidemiologic study designs with my supervisor, Norm Breslow. But I've become even more excited about it, about this area more general area called data integration, how to build models for when you have multiple data sets which may not have the same types of information. And sometimes you may not even have the actual data. You may have summary statistics. So that's my broad theme about today's topic. I know it's late in Friday, so I'm trying to be a little light on the technical side. So it'll be more of an overview of the methods and then some really recent applications that I hope will excite you guys. And so I work on that, a lot of disease risk prediction model, just to give a little bit of background that where I come from, that I am interested in developing model for predicting risk of disease. But of course, there are prediction models that are needed for other areas like for prognostic models, but I'm focusing a lot more on predicting among healthy people who might develop the disease in the future. And as many of you know about, like, for example, NIH, All of Us, and Precision Medicine Initiative, one of the goals of the precision medicine is on the prevention side. That means that we will be able to use big data sets like studies from the cohort like All of Us to eventually one day build a model with many risk factor informations, biomarkers, genetic factors to predict individuals' future risk of disease. And those could play a very critical role to sort of doing targeted intervention through screening or medication, preventive medications, and things like that. So that's where I come from when I develop disease prediction model. But obviously, that's this kind of the type of prediction model I'll be talking about has application in a lot of other areas, like predicting survival after disease and other settings. So with that in mind, so these are sort of the topics I would like to touch upon, but it's okay if I don't touch upon all of this. And as I said, I'd like to keep it a little lighter since it's getting late in the week. So I'll have, in the beginning, I'm going to talk about some general methodology framework, and I'll set up the problem. I will show like one cool application we have recently done of using some of the ideas from that framework. Not exactly that we had to come look at some corners, but nevertheless, the ideas were there from the general methods to develop a COVID-19 risk prediction model that we developed earlier this year. Actually, most of the work happened late last year. And then if I have time, I'll try to cover also polygenic risk modeling, which is also another very pertinent topic nowadays. Okay, so the heart of the matter is this. So we, traditionally we think that, we have a lot of methods, the classical regression methods to modern machine learning methods that allows you to develop complex predictive models, assuming that I have a single data set, or I may have multiple data sets which has harmonized data, and so that I can pool them. But a lot of the times, what we are facing nowadays is that we may have access to multiple data sets, and they might have collected disparate informations. And one classic example would be like nowadays, there are a lot of consortium of epidemiologic studies, for example, breast cancer epidemiologic studies, where there is a common goal. They want to understand risk factors for breast cancer, but different studies have been designed using different instruments, even different sampling mechanisms. And so they have collected also different kind of information on the confounders, the main exposures, and sometimes even the outcome, how much detailed outcome information has been collected may also vary. And the study design can also be variable across the studies. And as I said earlier, and so this is one kind of disparate data problem that we are often facing. And I'm sure in every field people faces this kind of problem. And then sometimes you might have this kind of disparate data problem by design, which is I was talking about the two-phase epidemiologic design, where you might have a large cohort study to begin with, but then you want to collect more detailed information on some biomarkers or some really brand new technology that could not be rolled out for the whole cohort. Then you can do some nested case control sampling on which you can measure those additional variables. And now if you think about your second phase sample and the first phase sample, that creates some disparate data problem, or you can also think about a missing data problem. Another issue especially comes with in the consortiums type of studies, but also it could also appear in two-phase design, is that there are a lot of complex logistical and ethical issues in sharing individual level data, and also there are proprietary issues that why people might be uncomfortable sharing total these individual level data across all of these consortium sites. And what could be much more easily available is that each study might do their own analysis using or whatever the information that is available and fit some kind of model, and that model, and they might be able to share those parameter estimates from those model and what we'll refer to generally as summary statistics from those data sets. And so, and there are other type of data sets, which is, it seems like very different, but it could be actually used for disease risk prediction model, where at least in the places I work on. So for example, for cancers, there are a lot of, the National Cancer Institute as well as CDC maintains very good cancer registries, which gives you information about the disease incidence rate, in the population. And that could be very useful for modeling absolute risk, but note that they are not linked to any covariate data. So it's completely the outcome data. That is like what is the distribution of your cancer incidence by age that's available, and maybe race and gender, but that's about it. You do not have covariate information. And then you also have CDC's data, various health survey data like NHANES and NHIS. There are wonderful data sets CDC makes it available, and they are kind of underutilized, I think. That gives you information of distribution of risk factors in the population, the general population, but they are not linked to the outcome. So they are only, these are the information on X, but no link with the outcome Y. Okay, and this is like information only on the outcome, but no link with the X. And so those are some valuable information that we can try to integrate in various types of analysis. And then increasingly there is also available large administrative health records from the electronic medical record systems. But I'm not going to talk too much about that, but some of the issues comes up there as well. And so so when you think about combining multiple data sets and then do some kind of uniform and unified analysis, the first thing that comes often to people's mind, the simple things, is doing a meta-analysis. And it's a very popular approach. It is widely used in every field, from clinical trials to epidemiology to GWAS. And one of the popularity of this approach is that it is logistically very convenient. That basically it involves only sharing summary level data. That means, again, whatever the parameters that you're interested in, target parameter, that could be the effect of an exposure or effect of a treatment, and you run your analysis, and then you share that information, that summary level information across your consortium and do meta-analysis. And also it has some nice statistical efficiency property that, and you can show that, that at least under some reasonable model assumptions, like for example, like there's the homogeneous effects across the covariates across different studies. Then if you do the meta-analysis versus if you actually did the pool analysis, the parameter estimates of those common effects that you will get, they will have similar efficiency, at least as asymptotically have the same efficiency. So you are not losing much by doing the meta-analysis. There are situations where you can lose efficiency also. And this is one of this reason, this meta-analysis type of approach has been also popular for this developing divide and conquer approach to divide up big data, run models, and then combine at the end. So that's the basic principle is the same. Okay, so let us look at then what's the simplest form of meta-analysis. And so if you have a set of parameters, that suppose this could be the parameters associated with the set of variable in your logistic regression model, and suppose you have a bunch of studies where all the variables were measured, and then you have a multivariate parameter vectors from each study, and then meta-analysis basically is the weighted least square estimate where you weight each set of parameter estimate by the inverse of the variance covariance matrix, and you normalize them. So this is a multivariate version of the simple meta-analysis. It's called the fixed effect meta-analysis. That is the optimal under the fixed effect model. But even if the fixed effect model was not correct, this may not be the optimal estimator, but it still has a reasonable interpretation that it is giving some kind of average effects. Even though the true effects were heterogeneous, that you are getting some kind of average effects over the different study with the weighted by the sample size of the different studies. So, so it's still a reasonable target parameter. Okay, so we have been developing and through a series of work, and most recent of this is, although there's been a more recent work, but this is the one of the more paper that showed the framework, is something called generalized meta-analysis. And before I describe what the statistical framework is, but let me describe what it does. And then we'll talk about how it does it. So it's a technique for estimating parameters associated with a multiple regression model. That means a regression model with multiple covariates, because there is sometimes confusion. What's multivariate regression model? What's a multiple regression model? So I'm talking about a single outcome, multiple explanatory variables. And it's through meta-analysis of studies, which may have, where each study may have only partial set of information, the regressors. And so what it produces is that it estimates the effect of each covariate in the model. It will produce a kind of a super model, Uber model, that will encompass all the variables that are included in at least one of those studies. And what it will produce, that the effect of each of those covariates in fully adjusted model that will adjust for all the effects of the other covariates. And the way the model will work is that we make some clever use of the relationship between a model, extended model, and reduced model, which will come back. And so you need information on those parameters from the various studies, but you also need another data set, which I call a reference data set, that allows you to estimate the joint distribution of all of the risk factors that are going into the final model. So that's called I call it a reference data set. I borrow the term because in genomic research, there are a lot of reference data set to estimate joint distribution of your SNPs. Like, for example, 1,000 genome data, but you can think about if you are doing epidemiologic work, you have a lot of risk factors. And one good reference data set could be some of the CDC survey data sets, which allows you to estimate joint distribution of risk factors, various health-related factors in the US populations. Okay, so now so that's what it does, but let me tell you how it does it. And again, the very basic outline. So you can think about, again, I'm talking about for the time being a parametric regression model, but it can be extended to non-parametric regression models, semi-parametric regression models, like the Cox model. And so, we have a model of the type we are trying to fit, trying to predict Y based on a bunch of variable X. And it's a parametric model like a logistic regression model or probit model or some kind of model. And then what I have is that as information from K different study, and what each study is providing estimates from parameters from a model that I call reduced model. So reduced model is like in a given study, they may have measured a subset of those variables. And based on that, they have fitted another parametric model. It might be the same logistic model, or it could be actually a totally different form of the model. It could be any type of model, as long as I know that what model they fitted. That's what I needed to know. And they're providing me the information on the estimate of the parameter and the variance covariance matrix. So that's the information I need. And this model does not have to be correct or even coherent with the bigger model. So for example, as we know, like if we start with the logistic regression model, then the reduced model may not be logistic regression, but that's okay. I mean, so this model does not need to be correct. So that is allowed. And then, of course, there's some basic identifiability condition, which is obvious that that you need to estimate so we need to have a data set to estimate the joint distribution of the risk factors in the population. That does not need to be linked to the outcome data. It can be information that allows you to estimate the joint distribution of the risk factor. That's called the reference data set. So what is the basic idea that we are using? The basic idea we are using was actually we kind of showed in this paper, which is where we proposed sort of how do you develop a kind of a more extended model when you have individual level data from a study on both set of variables like X and Z, but we want to make use of information on external information, on some reduced model parameter. Let's suppose that only involves X, and suppose that you don't have the individual level data from the external data, but you only have the parameters that are given to you, parameter estimates, and assuming there is a very large study. And so the main observation is that suppose if you ignore that information, you could of course do the standard maximum likelihood inference only on that space. But if you have been information on that, what is the value of a theta from a very large study, then you can basically think about there's a projection that if this is the correct probability distribution, and I'm assuming here that the full model is correctly specified. So I'm assuming that the true probability law belongs to that space of that parametric model. And if you make the projections into the reduced model space, that may not belong to that the parametric model that has been considered. As I said, this reduced model does not have to be a correct model, but that is okay. Because if somebody tells me like that suppose somebody has given me an estimate of the maximum likelihood estimate of the parameters from this reduced model, and then I know from my classical maximum likelihood theory that if this is the true probability distribution in the projected space, and this is the kind of the maximum likelihood from the kind of a misspecified model, there is actually a relationship between the two. And this is basically given by this maximum likelihood estimate basically tries to find that distribution in this space, which minimizes the Kullback likelihood distance between that point and the true probability law, right? So that means that I can use that kind of result, the observation, this is the classic Hoover's maximum likelihood under misspecified model theory, to make a connection between the parameters beta that I care about and the parameters of the reduced model. So that's basically the geometry of that how you connect parameters of a extended model and parameters of reduced model in arbitrary setting. And you actually can write down this some simple algebra mathematically, that you can show that there is a relationship between the parameters of the true parameters of the full model, that's the beta star here I'm assuming, and take any reduced model from a kth study, and that could be written. There is no explicit relationship between the parameters, but you can write down an implicit relationship through a set of integral equations, where these integral equations are defined in terms of this function u. And notice that u involves basically take the score equations for the reduced model, and it's the integral of that score equation with respect to the true probability distribution of y given x that is given by the full model, right? And so you can see that this equation establishes a relationship between your beta that you're trying to estimate and the reduced model parameter theta. But it does require the assumption that the full model is correct. That means y given x, the full model is correct, but it doesn't require any assumption about the reduced model being correct. But to identify these equations, these integrals, so you need to have an estimate of the distribution of x, nothing else. Right? If I given a theta hat from each study, I can write down an equation for that tries to identify the beta. But to identify the equation, I need to plug in an estimate of the F, the distribution of all the risk factors in the population, and that's why you need the reference data set to define these equations. So basically what happens is that then you take the reference data set. So for each study, so I can sort of, each study gives a set of these reduced model parameters, and that helps me to define these kind of vectors of the integral equations, and where the integral has been replaced by the empirical expectation based on the reference data set. And so you can think about as a vector, I'm kind of concatenating those U vectors from the different studies, and that's becoming a new kind of score type of vector, and then basically taking the empirical sum of those things over the distribution of X, which is coming from the reference data set. And notice that theta hat has been plugged in, which is coming from the external study, and this is helping me to identify the beta parameters. And in fact, what might happen is that you might have too much information, right? Because this number of equations here in this setting can become more than the number of parameters in the model. Suppose I'll give a simple example, like suppose I have 3 studies. The first study gives me information on X1 and X2. The second study gives me an X2 and X3. The third study gives me an X3 and X4. And so I have like, X1, X2, let's say X1, X2, X2, X3, and X1, X3. In the full model, I have 3 variables, 3 unknown parameters, but number of equations, I have 6. Because each study is giving me 2 equations. So, the vector or the dimension of U is same as the number of reduced model parameters. So that's what, so that's why the number of equations in this here can become a number of more than number of unknowns. But that's okay. We know how to solve those kind of things. That's where generalized method of moments come. So you cannot solve this equation exactly 0, but you can say that, okay, I'm trying to minimize that function and bring it closer to the 0 as much as possible in a quadratic distance sense. And so that's where the generalized method of moment comes. So you can choose any matrix C here, and that will, and then you try to minimize this function to get your estimate of beta. And then you can use the generalized method of moment, has a very beautiful asymptotic theories similar to the maximum likelihood, as rigorous as the maximum likelihood asymptotic theory, comes a lot from the econometric literature. You can use to develop the asymptotic theory of it. And then based on that, actually, you can choose, say, what is the optimal C? Okay, because any C will give you a consistent estimator. But you can choose an optimal C that minimizes the variance of this quantity. And that could be derived, and that will involve, of course, the unknown parameters, and you have to plug in, you have to come up with some initial estimate, you plug it in, and then you update it, and then you get the efficient estimator under this framework. And the nice thing is that, so this is sort of, we are minimizing, but suppose you have a high dimensional problem, it can be easily extended, right? So when instead of suppose I'm trying to do some now regularization, then you can add a penalty function on top of this, objective function. So that's sort of, at least, there are computational issues, how do you do it, and, things like that. But there is the avenue, like how to generalize this to high dimensional setting. Like you can do parameter regularization, but adding a penalty function to this objective function. So think about, this is kind of replacing your -2 log likelihood of your, and then you can add your penalty function. And in fact, you can also develop Bayesian methods. You can convert this to a quasi likelihood, this quantity, and then start putting prior on the beta to start making inference on the on those in a Bayesian framework. And some of those extensions for the GMM has been actually done, but not for these particular applications, but there are actually existing theory how to do penalized regression using GMM kind of objective function or Bayesian inference using a GMM type of objective function. So these things can become quite pretty general. By the way, feel free to stop me and ask questions. As I said, I don't have to finish all my slides. So I'll take a pause and see if anybody has any questions.
I have a question, actually,
Yeah.
and I'm glad that you paused on this slide. So I'm confused as to how this estimating equation, this UN, is unbiased if we are plugging in theta hats that may not be from a correct model.
Right. So the expected value of U is 0, number 1. And theta hat is a consistent estimator of whatever the theta is in, because that theta has an interpretation, even if it is a misspecified model, and theta is a consistent estimator of that parameter. Okay, so that's how you have to think about it. So expected value of u equal to 0, and theta is converging to some parameter value, which corresponds to the equation that reduced model equation solves in the population.
Okay, that was my other question. Does theta have to be consistent? So there you go. Thank you.
For that, whatever that quantity is, like, you know, if you have a misspecified model, and you can fit a misspecified model to the whole population, and suppose that equation has a solution, so you have to think about that. That is your sort of theta star, the true theta, and your estimate is converging to that parameter.
Okay, thank you. Yeah.
Any other questions? But that's a good question. It might be confusing. All right. So here is the schema. As I said, I'm not going to go too much about the asymptotic theory and everything, but just to remind you the schema, all you need is basically, again, if you are working in a cohort, consortium setting, if people can run their own analysis, based on whatever variables they have, create the parameter estimates and variance covariance matrices. We have shown that even sometimes, in the literature, if you're collecting that information from the literature, it's easy to get the standard error, but you may not have the covariances. And there is a little trick you can do to get the covariances from the reference data. And so that's nice. But if you are working with the, investigators of the study, you can push them to give you the covariance, not only the standard error, but the variance covariance matrix. And then you do the same thing for the study 2. And then you have the reference data set that you have to put some thought and work. Where do you generate the reference data set from? Is it going to be from one of the study, which has the most complete information, or is it some external source? So that there are some details there. But all of those things help starting to estimate, establish some estimating functions. Each study gets converted to an estimating functions, and you have a series of estimating function, and then you solve them using generalized method of moment. And then you have a subsequent asymptotic theory of that.
Can I ask a question about reference data set? Is it like we can relax this requirement for the reference data? This is because in some settings, we may not have this data available, right?
Right. I mean, you need some information on to estimate the joint distribution. Think about it. I'll give a simple example. I have, I want to fit a model with X1 and X2. Okay. And the first study has given me the association between Y and X1. And the second study has given me the association between Y and X2. And I'm fitting a model with X1 plus X2, right? Without knowing any information about what is the correlation between X1 and X2, I have no hope, right? Okay. So I have to, either, like get a reference data set. If you have a reference data set to estimate this distribution completely empirically, that is the best. But if you do not have that, you can combine multiple data set to try to estimate what that correlation might be. So there are ways you can go about trying to kind of simulate the reference data set as well. If you do not have a in practice, we might have had to do, like, combine multiple data set to create the reference data set that gives a reasonable distribution of the joint distribution of that risk factors. But it may involve some simulation as well.
Okay. Well, even if like the study 1 can provide X1 and X3, and the study 2 provide the distribution of X2 and X3, is it possible to identify the joint distribution of the X1, X2, X3?
Not unless you make a very strong assumption. Right. So here we are trying to keep the distribution of X to be very unspecified as much as possible. But yes, what I'm saying, in practice, you might have to make more assumptions if you do not have a reference data set to estimate that whole joint distribution non-parametrically.
Okay, thank you.
Okay, so of course, there are assumptions when you are doing that. So what is the biggest assumptions that you have to be careful about is that we are assuming that the homogeneity of the underlying risk model, that the full model, that beta y given x, that's the model we are trying to, this is the model, that the distribution of y given x, that regression model, is homogeneous across the populations, and we are trying to estimate that common parameters. And we are also assuming that, it's not an necessary assumption, but for the first iteration of it, we assume that they also have the same risk factor distribution across the populations, right? Because we are plugging in the same reference data set to estimate that integral for each study. Okay, but that's not a necessary assumption, right? So if you have some reference data set that is more representative of that population, you can use that one instead of having one same reference data set for all the population. Or you can come up with a lot of weighting techniques. You might have one reference data set, for example, from the enhance, but then you realize from your study that people are older, right, compared to the enhance. Then you might weight them back to the, that reference data set so that it reflects that study population. So there are things you can do to relax that assumption about the risk factor distribution being same across the populations. And so anyway, so one thing we thought is that since there are, of course, any kind of meta-analysis when you're doing, sort of a homogeneity assumption, it is good to have a test for heterogeneity. Like, in a standard meta-analysis, you have that test for heterogeneity that is often you report together with your meta-analysis. So we are able to show that you can actually, using the GMM framework, you can also have a test for heterogeneity that will give a combined test for, that is there any source of heterogeneity, either due to the risk model being different or the risk factor distribution being not correctly representative of those populations, the reference distributions. So if there are some gross violations of those assumptions, it should be able to detect it. But in practice, as we know that, of course, a test may lack power, and so we may not detect the differences, but there could be still some differences, and that can lead to some interpretational problems and things like that. So the usual meta-analysis problems you will have here as well. And as I said, like the reference data set assumption of that the same reference data set can be used for each study population that is actually can be relaxed. There are a lot, you can come up with a lot of calibration and weighting techniques to make the reference data set to be more representative of those study populations. So just a comment about basically, as I said, that this is where how to manage bias and efficiency for this kind of methods. So this is basically in the reference data set, you can adjust for study designs if the different studies have used different sampling designs, which is again different from the reference data set that can be taken into account into that expectation calculations. And like you have to case control design or other type of weighted design that could be accounted for there. And the efficiency comes from the choice of the C. Like, that if you get the variance covariance matrix of U, and if you can plug that in, when you do that U transpose CU, that is guaranteed to give you the efficient estimator. And so that's why you have to account for all the sources of uncertainty. If you have overlap between the study population and the reference data set, that extra covariance terms comes in, all of that goes into the C. As long as you can take into account all the sources of uncertainty and covariances and things like that, and you can calculate that, you can construct your efficient estimator. That's in that using the GMM framework. So that's how you basically manage the bias and the efficiency. And another point about the reference data set, there's a good question, sometimes it is hard to get the reference data set. And one of the interesting things we found that the reference data set does not need to be very large. It can be fairly small compared to your study sample sizes. And here are some sources we talked about, for epidemiologic risk factor, for example, enhance and the CDC survey data sets are very good data sets. If you're working on a consortium, there might be one study which has very complete data. You can use that data set and then weight them up according to the design of the different studies to create different reference data sets. So there are a lot of issues here, practical issues. But so here's some basic simulation studies. So again, this is a very, very, I would say toy simulation studies, but it makes some points, interesting points. So here's the situation. I have trying to fit a logistic regression model with 3 covariates, X1, X2, and X3. I have 3 studies. Study 1 provides X1, X2 parameters, and the study 2 provides X2 and X3, and study 3 provide X1 and X3. Okay, and then let's see so what I'm trying to show here is that and then I have basically that the first row where so it's all multivariate normal. The covariate distribution is a multivariate normal, and in the first situation, so there are sigma 1, sigma 2, sigma 3, and R, sigma R. This is the variance covariance matrix of the X matrix for the 3 studies and the reference population. The first situation is the ideal situation, which is sort of we assume that all the populations are exchangeable, the covariate distribution is the same, as you would expect that the results will be correct because the theory is correct. So the biases are negligible and good coverage probabilities are great, and that's what you would expect. And then the next set of situation, I start violating that distribution being equal in a lot of different ways. The first situation is that there are studies are homogeneous, but the reference data set that I've used is somewhat different, or or the studies are somewhat different from the reference data set, and so on, and so different combinations. And I have created those, if you look at the correlations that I sample those sigmas from, they are somewhat different. In this situation, the x1 and x2 is somewhat correlated, and then x2 and x3 is higher correlated, and there's very little correlation or zero correlation in between x1 and x3. In the second row I'm taking, it is again the order is the same, but the degree of correlation is more, and then in third situation the degree of correlation is even higher. Okay, so I'm trying to violate the in different ways, and then the main point is that of course I could create extreme situation. This is not extreme situation that that the correlations are entirely different. So the mean and variance, it didn't matter, so that I can tell you, like having different means and the variance of the x's doesn't make a big difference in these inferences. So what matters is the correlation, because that's the information that is getting fed in to correct for that, external sort of use external covariate information to adjust for the confounding. And so that's why the correlation is the more key player. And if you violate the correlation being very different, then you expect to start seeing some biases, and that's what you start seeing some biases. Like you can see that you will start seeing the more noticeable biases than the ideal situation. But still, we were, under reasonable assumption, you are finding that the biases are not that large, and the coverage probability still remains good. But of course, we can break the situation. And in the paper, we did break, and created more extreme situations to show that the bias can start creeping in. That's why you have to be careful about the assumption about the exchangeability, and try to make as much as possible with weighting and things like that to create more appropriate reference data set for each study. But the other point, which is more interesting point here, is that so here the sample size for the studies was the 3 studies was 300, 500, and 1,000. Okay, and what I'm showing is and how the mean square error for the parameter estimate changes if I keep the study sample sizes fixed, and then I change the sample size for the reference data set. And notice that what is happening, that it is reducing initially, but it kind of achieves a plateau pretty soon at 100. After that, it doesn't do much to have a larger sample size. And the reason being that these sample sizes are fixed, right? So the uncertainty estimate of these parameters depend on the sample size of this and the reference sample size. If I keep this fixed, then my mean square error cannot keep going down. And the point here is that it's pretty fast. This comes down, and it is like at 100, which is sort of 1/3 of the smallest study in the out of the 3 study. After which it doesn't make a much difference in the efficiency. So that's why the requirement for the sample sizes is there, but it does not have to be a huge sample size, compared to the study sample sizes. Okay, so that's sort of the general methods. And then, I think I'm going to do one application, which is so that I can do it in a kind of a more easier pace, which is the COVID-19 application. And this was a paper we published. Actually, the paper was published in the January of this year. But most of the work was done in the last year between summer to the fall. And so we developed a model, individualized kind of model for prediction model for predicting COVID-19 risk, mortality from COVID-19 in the general US population. And our motivation was that, by the time in the, I think, middle of 2020, by May or June of 2020, a lot of studies already started identifying risk factors for COVID-19 complications, mortality, or infections. And so that we already know that there are actually risk factors that by which people's chance of infection, people's chance of complications and mortality changes. But what was lacking was that a model for at least for the US population that will allow you to combine information on all the risk factors to estimate an individual's risk for, let's say, in this case, I was interested in predicting the ultimate mortality from COVID-19 among people who have not currently developed COVID-19 yet. So the idea is that people who are healthy, a bunch of risk factors, and then I'm trying to predict that what is the chance that the person might die one day from COVID-19, And so it captures the risk associated with both infection, complications, and the ultimate mortality. So all of them in one single model. And the reason this kind of general population models are interesting is that because this kind of model can be used, for example, vaccine prioritization or developing other kind of prevention strategies where you sort of think about which population you need to first target. And of course, vaccine, you give it to healthy people and to that who are the highest risk of ultimately dying from vaccine, or other kind of preventive effort that needs to be given for designed for healthy people. And so we kind of anticipated this, around the middle of the summer that, this kind of model would be useful to ultimately have it for the US populations. So we thought how can we do it? So this is on the background, as I was saying, that there are, potential applications that this kind of model might have. And that was, we are anticipating at that point, but we saw that, first of all, such a model is not available and there is not great data, at least in the US setting, to quickly develop such a model. Usually I would like to, if you have a question this for a cancer, I'll try to establish a large cohort studies, which will take me 10, 15 years. And then I'll have a very nice model from a large individual study. So here I'm I have to develop this in the next few months. And that's where the data integration tools came very, very useful. So what are the sources of the data we use? So there's one study, which is UK obviously is ahead in many of these things. And because of their healthcare systems, and they can do quickly, because of the national healthcare system, and they have records already available, detailed information on various type of risk factors and comorbid conditions and stuff like that. And that was linked. They linked quickly this to their COVID-19 deaths, and then they developed a model for the UK population, which includes sort of basic factors like age, gender, and race, various comorbid conditions, as well as measures of social deprivation index. So that was, I thought, a very good source of information. But of course, I cannot just take the UK model and apply to the US, because there are important differences between the UK and US, especially when it comes to the ethnic distribution in the US is different from the UK, obviously. And then also, although CDC and in the US, we are lacking data on these kind of detailed risk factors, but CDC was publishing good data on mortality from COVID-19 and infection by basic information like age, race, and gender. So we should be at least able to use those information, and those are for the whole population. So we should be able to at least, and they don't have the other covariates, but they have good data on those basic factors. And so our idea is to use this kind of data integration methods so that we can develop a model that is more calibrated for the US population, which will take information on the rate from the US and on the variables that we already have for US, and then assume that conditional on those factors, the other factors that we do not have, that like especially the effect of the comorbid conditions are similar between the US and UK population, conditional on the age and race. And so, but again, to do that kind of data integration, as I said, like we need a reference data set that will allow me to estimate the joint distribution of these factors in the US population. So what we did was that, again, CDC has very good data set, NHIS and NHANES, which combine those two to estimate what is the kind of joint distribution of these kind of factors. All the measures of health conditions and a particular measure of social deprivation index, which is not exactly the social deprivation index the UK was using, but we found a close approximation for the US. And we combined multiple data sets to come up with a reference data set so that we can develop an integrated model.
About 5 more minutes.
Yeah. Question?
Oh, I just said about 5 more minutes.
Okay. So that's sort of, just to show you some comparison between the UK and US. So this is sort of the basic age adjusted rate, basic age stratified rate of mortality from COVID-19 between the UK and the US without adjustment for any other covariates. So you can see actually they are pretty similar. The age effect was very similar across the two populations. And then the race is more harder to compare because of course, they do not have Hispanics, and then the Asian population in UK and Asian population in the US is quite different. But if you look at the Black versus white difference between the US and UK, you do see similar degree of Black versus white difference in mortality, and that was happening at least in the last year. Okay, so this is sort of like just to give you a flavor of what the generator did for us. So this is sort of think about like the covariate we had from CDC, the age and race, And if we had just, just suppose that if you look at what was the effect of the age and race would be using the CDC data only. And this is the kind of the effect we'll get from a kind of the Poisson regression model in terms of the hazard ratios. But these effects are not adjusted for the other risk factors, right? Because CDC is not accounting for the other risk factors. So GenMeta, which is tried to combine the age effects and gender race effects taken from the CDC with the other parameters of the UK model, which accounts for the pre-existing condition, what you start seeing is that what you kind of expect that the other pre-existing conditions will start explaining part of the effect of the age. So you can see that is getting attenuated, like as you would expect, because as you get older, you have pre-existing conditions, and pre-existing conditions are explaining some of the things. The age effect is getting attenuated, but it is nowhere, it is disappearing. Same story with the racial disparity, that some of the pre-existing conditions are actually explaining part of the racial disparity, but a small fraction of the racial disparity. It is still, you have a lot of racial disparity left. That means those pre-existing conditions cannot explain those differences. Okay, another cool thing, I think, again, I will not have a chance to go over in detail, is that, so that's sort of the, kind of the relative risk model that, that we developed using the GenMeta. But then we said, okay, it'll be nice to have an absolute risk model. That means that, okay, you have, this is your risk factors. But now with the same risk factors, if you are living in Florida versus if you are living in, New England, you might have a very different absolute risk of mortality, because the current infection rate and the current pandemic scenarios are very different. And so how do we get that information? So, but what we found was that obviously at that time, there are a lot of pandemic forecasting models. They are forecasting what is the future overall kind of the population average death rate is going to be by different states. Okay, so we kind of combine this kind of the relative risk model, this kind of the model that we developed using the GenMeta. And again, we use some kind of calibration technique to now that will allow you to not only take individual risk factor information, but also the state of residence to produce an absolute risk of, let's say, mortality over the, let's say, next 3 weeks or the next 2 months, depending on how much the forecasting model allows you to predict. And that will be individualized. That means that will account for the individual risk factors, but that will also account for where that person lives, to say that what is that person's likely mortality from COVID-19 in the future. I'm not going to go into the detail how we did it. There's a kind of a nice calibration you can do. Again, you can think of as another data integration technique, because the forecasting model has no covariate information, right? They're giving the population average estimate of the mortality. And then I have the individual level model, which is sort of covariate information included. So again, you have to do one more calibration step to put them into the same framework. And then we developed a tool, basically sort of web-based tool, but easily accessible to the mobile also. And that allows you basically sort of, you can give information on individual risk factor profile and do the calculation. First, it will based on relative risk, and will produce a relative risk compared to the US average risk, and put them in the very high risk to high to substantially elevated, moderately, and some close to average risk, the populations. And that tool got, like, when we released the tool, it was at the height of when a lot of the vaccine prioritization discussion was happening. And so we suddenly saw a huge flood of people coming into our tools. I think we had, like, within a few weeks or a couple of months or so, we had a couple of million visitors visiting that website. And then the other thing we showed that, suppose if you had that, actually, there was a lot of discussion about, like at that point, that who should get vaccinated, and then the CDC was coming up with guidelines. And then again, there was similar discussion going on, like who should get the booster shot and things like that. So one strategy, I don't think that's the only strategy, but it's piece of the strategy, that it should be based on risk, right? People who have the highest risk of mortality, they should get some kind of priority. But there are other criteria as well, like, because this infectious disease, some people may decide to get vaccinated those people first who has highest chance of infecting other people, right? That's where the frontline workers come. So that's one piece of the problem. But there's another piece of the problem, is that people should be vaccinated who themselves has the highest risk of mortality. And so we did some projections for the US, like say, okay, how many people in the US living in the adult population who are in these different risk categories? That the very high to medium high to, and this kind of thing. So these are our estimates. And those estimates we get by applying the model to CDC datasets. We can estimate how many people are there in each category. And then based on the model's discriminatory accuracy, which was pretty high, And we can estimate, if we suppose we have a target the vaccine in the first, the first 1.6% of the population of 5.4 million population, and if we give it to them and the vaccine was 100% efficacious, what proportion of death we will save? This is showing that, for example, if those are under those assumptions, let's suppose that there was initially limited amount of vaccines, I can give only close to 4% of the US population. And if we give that 4% of the vaccine to the highest 4% risk population, then we'll save up to 40, almost 50% of the death. And the reason is that, that the model is pretty good. And obviously age itself is such a strong risk factor, that if you do age-based vaccination, it will save a lot of life. And then the additional risk factors actually contribute. So anyways, I'll kind of skip some of the things, but I hope I could give you some flavor of the exciting applications about that. And it is because of the, this kind of data integration tools that we were able to develop this model so quickly. It was not possible if we were waiting for some kind of large data set that will become available, and then of course the opportunities, some of the decisions we are trying to make, we cannot make those kind of decisions. So to summarize, I just wanted to say, I'm very excited because this is, I think, a kind of a branch of statistics is going to be more and more important in the future. It has a tremendous opportunity to build complex model using data information from data or information. I distinguish between data information because you can have individual level data and you can have summary level information, and you can take advantage of both of them across multiple disparate data sets. And obviously, you need more assumptions, because of the, that you're trying to combine heterogeneous sources of data, exchangeability, and a lot of things. So you have to think carefully about the assumptions, and I think you need more assumption than having if you're trying to develop this model from a single data set, where at least you can claim that your model is valid to the internal population. Whereas you're trying to stitch together a model using information from multiple population, you have to think about what's the target population and what's the assumptions. And so I think that's why it's very key that after you've developed model, you do some kind of validation effort for the target population where you're trying to apply to the model for prediction and things like that. And then, as I said, so far I was talking about obviously building additive model, right? And I'm saying just take the variables from each studies and put them in an additive format. But you don't have to have additive model. You can start putting interactions as long as you can put any interaction terms between variables which have been measured within a study. Of course, I cannot input interaction terms between variables which are only measured across 2 studies, because you never could observe what is the nature of the interaction. But as long as you have observed some interaction terms within a study, you can start putting more interaction terms in the model. So that the method is also general for that. So with that, I hope I created enough enthusiasm about this field, and I'm happy to take questions.
Excellent. Well, thank you so much. Yeah, I'll open the floor if there are any questions. I can get us started. So I have a question about your COVID-19 risk calculator. I was wondering if you accounted for any of the information that is known about either vaccine efficacy or any of the publicly available information on trials. I know that that's sort of limited.
Right. So currently, so when you develop the model, the vaccines were not available. And then the models, the way models develop, it is currently for unvaccinated people, to sort of thing. But we haven't tried to incorporate now that people have, potentially it is possible that you can try to incorporate now that people have been vaccinated and we know the vaccine efficacy, start integrating those parameters in the model. And again, I think the data integration framework could be very useful because we will not have all of the information on a single study. So you can synthesize data from clinical trial, you can synthesize data from risk factor epidemiology, and then try to start putting them in one single framework. But we didn't do it.
That'd be really interesting.
Yeah.
Anybody else have any questions? I have another question. So this is earlier in your setup when you were introducing your generalized meta-analysis, and you had this setup where you had multiple studies. And I guess I was wondering if the fact that you can have a misspecified model, would this account for in any way sort of informative sampling of these different studies, right? So the fact that these studies may have been selected very differently or designed very differently.
I mean, like, for example, like say case control studies or cohort studies, sampling, talking about sampling designs.
Mm-hmm.
I mean, I think if it is coming from the difference in sampling design, you have to be a little careful, because one of the things, like, if the sampling designs are different, the full model I'm talking about, like, remember, one of the assumption is that there is a full model and which is sort of homogeneous across the population. That assumption can start getting violated.
Yeah.
Right? That model has to be cracked, right? I said, and then, because, for example, you have a case control study and a cohort study, right? And then we already know that under case control design, the full model, the intercept parameter has changed, right? And so then, then if I have not taken into account the design, so I shouldn't assume that the intercept parameter is the same, right? So that's why I think if differences is, there's some design issues that is coming because of the sampling design. And if you know those design issues, then I think we should take into account the weights and things like that, so that, after weighting, we can assume that they are the same.
Okay. So I'm really interested in this question of how you can figure out if you can combine, right? So a test, or whether, trying to learn the homogeneity, I guess, of these different studies. Have you thought about any of these extensions in your work?
No, I think that's a very good question. I think the framework is very flexible. So, like as I said, like this relationship we described, it's a very general relationship, so you can, for example, set up this kind of models, so that you do not assume that, you can set up your kind of reduced model and full model in a way so that what you are transporting is less, that you don't have to assume that all the parameters are transportable and things like that. So you can make, you can come up with a model that are kind of more flexible in terms of what you are borrowing and what you are not borrowing. But you can still use this theory to make the inference that there is always, you can write down a relationship between a, broader, bigger model and a smaller model. Okay. And now what is that bigger model and smaller model would be, you can choose so that you have more flexibility, that, that maybe not everything is transportable. There are some parameters which are, more likely to be, exchangeable, but some other parameters are not. Then you can cleverly set up your models. So, but I think that's an interesting avenue to explore, like, like the how, and I think this is where, also like there's kind of some of the transfer learning ideas and things like that can be very useful, like what, so you can specify your reduced model in a way, and so that the assumption, there are certain assumptions, there are some parameters which are transportable and some other parameters which are not transportable. So you want to leave them kind of, unspecified.
Yeah, that sounds really interesting. Well, thank you very much. I don't know if anybody else has any questions. Now's the time. Okay, well, thank you very much. That was a really interesting talk, and it's a real pleasure to have you. So thank you so much.
Thank you very much.
All right, bye everyone.
Bye.